of our best professionals in the field, and also have an impact on us being able to see that our students are exposed to best industry practices, interact with professionals who are doing the real live work there in industry. And we are fortunate today to have in our midst the Chief Engineer of eThekwini Municipality Electricity as our guest lecturer today. And that is the person of Dr. Sanjeeth Sewchurran. Dr. Sanjeeth Sewchurran holds, of course, a PhD from the University of KwaZulu-Natal, and he has, tremendous, accolade that goes with his entire record, which I think Dr. Tunji may introduce a bit more later on, but he'll be speaking to us on the drivers, opportunities, and challenges of solar PV projects within the municipality in South Africa. And I would just want to welcome Dr. Sanjeeth and thank you very much for taking time off to be with us and to share with us, and to thank all my colleagues, postgrads, researchers, postdocs who are online and others who are trying to get online right now. This meeting is being recorded, so that many people are going to actually see the recorded version because of their lectures, timetables, and so forth. So let me just hand over to Dr. Tunji, who is the organizer, and a few remarks to make, and then we'll go straight to the guest lecture. Thank you.
Thank you so much, Prof.
Yes.
On behalf of Professor Davidson, again, we are welcome to this 2021 industry guest lecture by Dr. Sanjeeth Sewchurran. I will just go ahead and read the biography of our guest lecturer.
Thank you.
Dr. Sanjeeth Sewchurran holds a Bachelor of Science, Master of Science, and Doctor of Philosophy degrees in Electrical Engineering from the University of KwaZulu-Natal, UKZN. Is a member of South African Institute of Electrical Engineers, SAIE, and also registered as professional engineer with Engineering Council of South Africa, and is currently the Chief Engineer at eThekwini Municipality Electricity Department. Is a member of SIGRI Active Distribution System and Distributed Energy Resources Work Group, and also a member of NRS 097 Grid Integration of Small Scale Embedded Generation Work Group, and also a member of Renewable Energy Technical Evaluation Committee, RETC, and C40 Climate Change Clean Energy Committee, and is the chairman of eThekwini Electricity Future Technology and Diversification Work Group. He has received numerous awards on work done in engineering field, which include the SAIE KETS Plodding Young Achievers Award, and also ESCOM System Operators Manager Award in the category of Excellence, and also EXA Award for Postgraduate Research, and SIGRI Best Paper Award, and also Clemson University Power System Conference Best Paper Award. He currently serves as co-supervisor and industry mentor for an examiner for undergraduate and postgraduate students at UKZN, DUT, and Mangosuthu University of Technology, MUT. So he's an industry advisory board member at MUT and adjunct research fellow at Durban University of Technology. So I introduce to you Dr. Sanjeeth Sewchurran. Please, you can proceed and share your screen. Thank you so much.
Thank you very much.
Good afternoon, colleagues. Thanks, Doctor, and thanks, Prof, for that introduction.
Most welcome, sir. Thank you.
Please let me know once you're able to see my presentation.
Okay. Yes, we can see it.
You can see it. Let me just try and get it. Is it in slideshow mode on your side, Prof?
Yes, that's right.
Okay, so I can't see if anyone raises their hand, so please just, yeah, Prof, if you could just let me know if anyone has any questions, or guys, you could just speak up, yeah.
Okay.
Okay, so thanks colleagues and good afternoon. Thanks for having me here to talk about solar PV. So my topic for this afternoon is drivers, opportunities and challenges of solar PV projects within municipalities in South Africa. So obviously because I work for a municipality, so the topic, obviously I look at it from a municipal point of view, but also we look at it from a customer point of view. And I'll explain why we selected solar PV as opposed to other technology for this presentation. Okay, so the presentation will cover a brief introduction. Then we look at what are the driving factors for small-scale embedded generation, or we'll focus mostly on solar PV technology here. Thereafter, we look at the factors influencing solar PV production, both in Durban and obviously around the country or world. And we look at what are some of the opportunities for solar PV projects and what are some of the challenges that we face as the municipality when we're integrating these projects into the grid. We'll just touch on it briefly, and then we'll conclude.
Thank you.
So I think, as we all know, there is an energy revolution currently underway, which municipalities cannot ignore. The revenue model on which the utility business is based is under a major threat. If we look on the left-hand side of the slide, we see that traditionally, municipalities used to purchase electricity from Eskom, then they'll transmit, transform, and distribute to their customers. At the end of the month, they'll basically read the meter and give the customer a bill, which he'll pay. So your profits are basically the cost of the electricity and the cost to supply to the customer, and the difference between what the customer pays and what it costs to supply the electricity. But I think with the fourth industrial revolution, which underpins the energy revolution, is already been witnessed by utilities as decarbonization, decentralization, and digitalization are starting to affect their traditional strategies. If we look on the right, our customers are actually no longer even called customers or consumers. They're called prosumers because they're generating their own electricity. So at any point in the day, they may be using their own electricity, or alternatively, they could be using electricity from the grid, or they could be exporting electricity to the grid. And customers obviously are demanding that they be remunerated for the electricity that they export to the grid. And typically, they want to use the grid as a large battery to store energy and obviously use energy as and when required. So my topic for today obviously touches, as I mentioned, solar PV. The reason for this is that this seems to be a technology of choice amongst our customers, whether it's in Durban or other municipalities around the country here. So there are a number of reasons why this technology has been chosen, which we'll cover in the presentation now. These are all projects that are currently installed in Durban itself. Okay, so solar PV connections on the eThekwini electricity distribution network, what we're starting to see is it growing at an exponential pace. If we look at basically 2021, we can see that we have applications for about 45 megawatts of solar PV to be connected to our grid, which obviously are at various stages. Some have been implemented, some are in the assessment stage, some are we still basically doing grid impact studies, so various stages there. So what is really causing such an exponential growth in the PV sector? So one of the factors is that the changing regulations. Previously, in the early days, it used to be generation license exemptions. Any project up to 100 kilowatts were exempt from getting a generation license. Later on, around 2018, between 2018 and 2019, it got moved to 1 megawatt threshold. And I think as of 2021, this limit has moved within the last month or two. I can't remember the exact date. It's been moved to 100 megawatts. So what we're starting to see is customers putting in larger projects here. Even if previously they installed a 1 megawatt PV system on a mall, they're coming back and saying, okay, guys, we want to install 4 megawatts or 5 megawatts, even up to 6 megawatts based on the available space there. So what is the reason for customers installing solar PV? So there's an example of, first reason is that customers installing it for their own use. There's an example of a shopping center where they have a 2 megawatt or MVA municipal supply. They install a 1 megawatt PV system. Typically what really happens is that if we can see the load profile here, the PV will supply a portion of the customer's load during the day. and the rest of the electricity will be supplied from the grid. There is no excess energy that will be exported to the grid at any point in time. The second reason is the customers install for their own use, to supplement their own use, and then excess is exported to the grid. This typically we see happens in the residential homes where there's the residential peaks, electricity usage peaks are in the morning and the afternoon, while PV, the generation peak is around midday. So because no one's at home and the electricity usage is lower, we find excess export to the grid. I think the same we also find a lot in terms of offices and industries that will use all of the energy during the weekday, as in the first case, but on weekends when they actually close for business, they tend to export bulk of their electricity back into the grid. So obviously these excess energy that's been exported to the grid can in future be used for charging of batteries should the customer install batteries. But at the moment, I think battery prices are still a bit expensive, so we're not seeing too much of batteries being installed. So guys are going purely grid-tied PV systems. Okay, so the next question we ask ourselves is, why is solar PV so is becoming the technology of choice, and why are we seeing so many projects? So I think some of the answers obviously will be that the technology is very simple. There's no moving parts and hence minimal maintenance as opposed to rotating machines where it has a lot more maintenance and much more complex. It's also modular, so capacity can be easily increased with additional panels and inverters. As explained earlier, customers obviously install systems, 1 megawatt systems, because of the licensing or they didn't need to license it previously. But now that the licensing threshold has been increased to 100 megawatts, they're starting to increase based on the space that's available. They can obviously increase the capacity. So it's not like buying one large generator and then should you want to increase the capacity, you got to purchase another generator as opposed to. So it's just adding additional panels, adding more inverters, and then linking it up to their existing system. So PV panels typically have a 25-year lifespan. So they last a long time. And obviously your inverters have a shorter time, starting from over 5-year warranties up to 10, 12 years, but they all can be extended at an additional cost up to 20, 25 years, depending on the brand. Okay. So there's short lead times here. We've seen 1 megawatt PV systems being installed in 6 to 8 weeks here. I think the biggest time that it takes is generally the procurement or to get the infrastructure in here. It's also renewable, meaning that it's effectively infinite energy source. It's coming from the sun. The cost of solar PV has been reducing over years. We've seen over the past few years, the costs have really come down quite substantially. Lots of panel manufacturers, which we'll cover later on, offers production warranties of up to 30 years. So typically they will guarantee that the panels would generate up to 80% of its rating after 30 years. And the fuel source, as we said, the sun is effectively free. So what are the drivers of solar PV? Let's touch on some of the drivers. So I think the first driver, which is quite or known to everyone, is the tariff increases. If you look at the graph in terms of the Eskom tariff increases, Eskom tariff increase pretty much followed the inflation rate up to about 2007. It was more in line with inflation. But in 2008, when the energy crisis started and load shedding started, then we started to see that the Eskom tariff increases went up substantially. So if we look at on the left-hand side, you can see between 2007 and 2019, while inflation went up 98%, Eskom tariffs went up 446%. So we can see substantial increases in the Eskom tariff compared to the inflation rate. So let's go back to Durban now. Looking at the tariff increase at eThekwini electricity from 2009 up to 2021, sorry. We can see that the average increase over the past 13 years was 12.1%. The highest increase in 2009-2010 financial year of 26.2%, and the lowest in the 2017-2018 financial year of 1.88%. So we can see that the increases are quite substantial, and obviously that builds up a good case to install solar PV. So obviously from the South African Revenue Services, there is tax breaks for customers who install solar PV systems. So for systems below 1 megawatt or up to 1 megawatt, they could basically depreciate the cost of the PV system up in the first year. So this typically allows up to 28% of the cost of the system to be depreciated by the company's tax in the first year of use, while systems that are larger than 1 megawatt, it can be depreciated over a 3-year period. So typically they can depreciate 50% in the first year, 30% in the second year, and 20% in the third year. So obviously this will help the customer as well, because they're getting tax breaks for installing a PV system that would supply them with electricity. In terms of funding for these customers to obviously purchase these systems, there is an upfront cost. So we looked at the leading banks in South Africa, the 4 leading banks, and they all support renewable energy projects, and they offer various funding options in terms of the loan period between 5 to 10 years, in terms of sizing of the systems, and in terms of the amount here. Obviously, the interest rate is based on its risk dependent here. So there is options in terms of obtaining funding. So if you're a business owner and you want to install a PV system and you don't have the funds, you could go to a financial institute, and based on the risk assessment, they would obviously give you a loan, which you could pay off in 5 to 10 years, and based on the fact that your system would last you longer than that. So there are other funding options, obviously, if you don't want to take a loan. So there is what we call renting of roof schemes, where the installer will pay the building owner to rent his roof. So the owner can use some of the energy that's been generated by the system, which he will pay the installer for. And alternatively, the excess energy would either be fed or sold to the municipality, or it could be billed to other customers. So whilst the PV system installer is responsible for system maintenance and operation and insurance. So the building owner basically gets paid for renting out his roof, and he's not responsible for anything else. The second option is equipment leasing. So in this model, typically the customer will pay a fixed monthly charge to lease the equipment over the life of the project, and all of the generated electricity is for the customer's consumption. So typically, whatever the system, he pays a fixed monthly charge for the duration of the project, and whatever energy is generated every month, he's able to consume it. And the last option, which seems quite common amongst our customers, if they don't obviously opt for the option of buying the system outright and owning it or financing it, is the PPA or power purchase agreement route, where the installer will provide his own financing and the customer signs a power purchase agreement. Typically, what we've seen is at rates maybe 10 to 20% below the current municipal rates, and they will sign a 10 to 20 year, depending on the PPA agreement. And then after that time, the installer either hands over the system to the customer free of charge, or alternatively, the system is sold to the customer. So for the duration of the PPA, the installation be fully maintained, and all charges will be picked up by the installer. So the only thing is the owner will allow the installer to use his roof for free, and obviously he will pay a lower than municipal rate. Okay, so what we also see is that when it comes to customers installing solar PV, we see that with the business and our industrial customers, the PV profile or generation profile, you can see the green curve, really matches the customer's load profile, in the sense that in the morning at about 6 o'clock, the customer starts ramping up either production or the air conditioning, or come to work, or sort of. And then we see that the load demand goes up until late afternoon, where it drops, where everyone goes home. So typically, your PV profile fits nicely within the customer's load profile, and all of the energy that's generated from the PV system can be used by the customer. So it offsets his energy purchased from the utility. So what we're also seeing is that obviously some publications done by the International Energy Agency, which now classifies solar as the cheapest electricity generation in terms of cost. And so obviously that will drive the installation of these projects and more of these projects since it's much cheaper now. So they'll obviously tie back to the reducing cost of solar PV itself, rising electricity costs as well. So let's look at some of the pricing structures. So Chile recently went out on an auction, and the lowest bid that they received in terms of the conversion from the dollar to rand is 20 cents per kilowatt hour. Whilst in the South African context, in terms of the 2.6 gigawatt renewable tender that recently closed, we've received, the lowest bid we received was 38 cents per kilowatt hour. So these are substantially low cost when you compare to other technologies, even if it's coal, nuclear, or obviously hydro or whatever technology. These are really cheap costs here in comparison. So the costs are obviously reducing here. We've done a recent study from a customer wanting to install a solar PV system, and we did some quick rough maths, and what we found out that it typically over a 30-year life of the project, it will cost him, the levelized cost of electricity will be like 52 cents in Durban. So whilst he's obviously saving 1,100 tons of CO2 emissions, we obviously took into account that he could depreciate, accelerated depreciation benefit from the South African Revenue Services of almost 2 million rand. So the cost of electricity is definitely lower than the cost of energy that the customer will purchase from the grid. And the cost of electricity from the grid obviously is going to increase going forward. In terms of how much, that's all we don't know. So what we did is we also did a few studies for the different customer categories. On the top left, we basically looked at a typical residential customer, and we looked at if he had to install a PV system. And in all of the cases, we assumed that the customer used all of the electricity, meaning that he sized his system correctly so that he used all of the generated electricity as opposed to exporting energy to the grid. Yeah. So what we did was we did for a wide range of tariff increases that we predicted over the next couple of years. So we looked at 3% up to 18% in 3% increments. And we can see that in the residential sector, it's typically 3 to 4 years payback period. Yeah. So that will obviously depend in terms of what will be the actual year-on-year tariff increase there. In the business sector, it's exactly the same, 3 to 4 years payback period, also dependent largely on the customers or the electricity tariff going forward. And in this case as well, we assume that the customer used all of the electricity. So in the case where the customer is exporting energy back to the grid, etc., the payback period increases slightly. Yeah. And in terms of the bulk customer category, these are typically our time of use, large industrial and commercial customers. The payback period here is between 4 to 5 years. So overall, for all of the customer classes at eThekwini, we can be seeing that a 3 to 5 year payback period for these PV systems. So the other driver is that carbon taxes were introduced recently, and the carbon taxes typically work on a polluter pay principle. So the figures that we've seen was it's 120 Rand per ton of CO2. And remember on the previous project where we looked at the levelized cost of electricity, that project generated 1,100 tons of CO2 in the first year. So it's quite substantial, but in the first round of the carbon taxes, we see that there's like 60 to 95% discounts on the per ton of CO2 emitted, so that the cost basically drops to 6 Rand to 48 Rand a ton. But still substantially, you could save substantially if you install solar PV systems. The other aspects is that customers have expressed environmental concerns with regards to using electricity from the grid, which typically comes from Eskom, either bulk of the generation from coal-fired power stations, the one nuclear power station, your open cycle gas turbines, up to hydro schemes. So overall, we see that for every kilowatt hour of electricity that we use from the grid, it has environmental impacts in terms of carbon emissions, sulfur emissions, and coal and other aspects. So customers want to try and avoid using the so-called dirty energy from the grid. And we see one of our customers in eThekwini, MAN Trucks and Bus, their truck and bus assembly plant in Westmead. They launched their first carbon neutral assembly plant in Africa. So they've basically covered their entire roof in solar PV. And according to their calculations, all of the energy that's generated by the PV system and all of the energy that we use during the year is basically able to offset itself, so claiming to be carbon neutral. So these are obviously not the only customers. So if we look further, South African breweries, they've basically announced that there's a new multi-billion rand energy project at their different breweries. So they obviously want to move away from the Eskom grid and the impacts of load shedding. Tetra Pak, that's another company in Pinetown, is committed to move to net zero emissions, meaning that they want to be carbon neutral. And maybe just touch on Toyota, that's in Prospecton. They obviously have ambitious targets as well. So they want zero CO2 emissions. So by 2050, they want solar energy to generate more than a fifth of their electricity. Yeah, so they want to be carbon neutral, reduce their emissions. And they have a lot of roof space. So if we're looking at the photo there, that's the Toyota plant in Prospecton. They currently do have some solar PV systems, but I think the plan is to obviously expand and install much more. So I think the solar PV correction, they want solar PV to generate a fifth of the electricity by 2025, actually not 2050. I think 2050 is they want to be carbon neutral. So the other driving factor is that there are a lot of businesses out there that have very large roof spaces, like on the top right-hand side and the bottom is your Gateway Shopping Center. So they have large roof spaces, which are currently not used for anything. I mean, on the roofs, you may find one or two aircon plant units, but that's about it. The roofs are unused space. So they could either install their own PV generation systems, or alternatively, they could rent the roofs out and get some money out of it. These are typically unused spaces. And then I think something which we're all familiar with is the under-frequency load shedding. So typically under-frequency load shedding is where your load demand exceeds the generation on the network, available on the network. And I think a lot of us have encountered this in terms of studying or trying to do work using candles and other sources of light to basically during load shedding. And obviously experience the challenges as well, such as driving when there is no traffic lights and lifts are not working in buildings, we have to use stairs. So I think this is another driving factor where customers want to try and see how they could mitigate against these energy shortages and under frequency load shedding. So typically your grid-tied solar PV systems will not help you during load shedding. So here's a typical good example of a grid-tied PV system and what happens during load shedding. So we can see the red typically shows your grid supply that's supplying the customer's load. Green is the solar PV system that's supplying the customer's load. And the gray area is typically your 2-hour load shedding block. So when load shedding starts, the grid obviously goes off, the solar PV goes off as well. When the grid comes back on, then it takes about 60 seconds for the grid to stabilize before your PV system is allowed to come back online. So your PV system is typically not going to help you with load shedding. But what we're finding is that customers obviously are using standby generators to generate electricity during load shedding and network outages. So typically what customers are now doing is that when there is load shedding or network outages, they use an automatic changeover switch that will disconnect the utility network and then switch on the standby generators to supply the load. So once the standby generators come back online and they are stabilized, the PV system will then synchronize to the standby generator, use it as a grid reference, and continue generating and supplying the load. Obviously, that's during sunlight hours. But what this helps the customers with is they reduce their running costs of their diesel generators. Typically 4 to 6 rand to generate electricity from a diesel generator. And as we saw, it's pretty cheap. It's much cheaper in terms from your solar PV system. So ultimately, it would reduce the cost of supplying your loads during the load shedding or during outage. So PV systems can be coupled with other sources of energy, such as this example where it's used in a microgrid situation to feed a mine. Obviously, this is not in Durban, but you can see that it consists of a 23 megawatt power station incorporating gas generators, a large PV system or PV farm here, diesel generators, 18 megawatts of wind, and a 30 megawatt battery and an advanced microgrid control system. So you can see this is typical standalone system where it's not dependent on the grid. So PV can be used with other forms of energy storage as well. So not only conventional storages, but we have compressed air storage systems where typically air is compressed and stored in underground chambers using electricity. And when it's required, it then releases it to power turbines or generators. There's obviously redox flow batteries, which uses a chemical reaction. Then you've got superconducting magnetic energy storage, which stores energy in magnetic fields, pumped heat electricity storage systems, and advanced rail energy storage systems, which typically what it does is when there is energy, it's then used to drive or power the axle drive motors on rail cars, pushing masses up hill and against gravity to a storage yard. And when it needs to extract the energy from the system, the rail cars move back downhill this time, and the wheels act as a tiny generator sending electricity back to the grid. And obviously, there's gravity-based energy storage towers, which obviously use electricity to raise up weights. And when there is electricity, and when electricity is required, it then lowers these things and it then generates electricity. So there's multiple energy storage forms and storage systems out there currently. They're still pretty new on the market, but I think the most common storage facility that's used with solar PV is obviously battery storage systems. So I've showed 2 examples here. These are systems installed in Durban. The top one, the top left-hand side is a 704 kilowatt hour battery energy system coupled to a 150 kilowatt rooftop solar PV system and a diesel generator. It's obviously coupled to the grid and has a UPS as well at UKZN. So this typically feeds the university's IT network and servers so that it's not affected by power outages or disruptions on the network. And then the bottom one is a 250 kilowatt hour battery energy system that's coupled to a carport solar PV system. And this is typically used to feed the customer that has critical load also with his diesel generators there. So as mentioned, that the cost of battery storage is still expensive. So, but looking at some of the work done by the CSIR, they predict that the cost of battery storage systems are going to reduce going forward. So I think just like how the solar PV systems started off, the costs were pretty high and we never used to see too much of these systems out there. But with time and as demand grew, we started to see that the prices have dropped substantially. So the same is going to happen with battery storage, according to predictions from the CSIR. So battery systems can be used for many reasons by the customer. So the first reason is what we call energy arbitrage. So if we look at it's called the industrial time of use tariff structure. So if we look at the top where we have, it's called the high season, between June and August, where it's typically winter in South Africa and the demand for electricity is much higher. So Eskom has to use much more expensive generation sources such as open cycle gas turbines, pump storage schemes to generate electricity to meet the peak demands. So if we look at the round wheel, it typically shows your peak times, your standard times, and your off-peak times, which correlate to the energy rates on the top. So we can see that in the high season or winter season, June to August, your rates are much higher. Winter peak is basically 4.07 cents, and that excludes VAT. That's the cost of energy. So what really can happen is that if the customer can charge his batteries at the off-peak energy rate of 76.51 cents, and you can obviously discharge that into his network at during a peak time, it's basically so your ratio of your peak to off-peak is 533%. So it's a substantial saving for the customer. If you can charge his batteries and obviously off-peak and discharge during peak, whilst in the summer months or low season, which is September to May, the rates are not as lucrative. So it's if you look at the ratio of your peak to your off-peak, it's only about 2 rand or 208%, which is much lower compared to the 533%. But if we look at that, if we look at the customer's load profile on this slide, we can see this is the annual 1-year load profile. We can see that between June and August, the customer's load demand is much lower. This is typically based on the fact that the cooling required by the customer is much lower in winter because of the lower temperatures and it's not as hot versus summer where you've got a very hot weather and you need your cooling systems require a lot more energy to cool the buildings. So typically what the customer can do is during winter, they can basically use energy arbitrage to charge during your off-peak and then discharge during your peak times to save on the 533%. And during summer, they can use what's called peak shaving. So typically on this tariff, you've got a network demand charge, which is 109 Rand per kVA, and you have a network access charge with 36 Rand per kVA. So what you can do is you can look at the white line on the top. So what you can do is anything above the white line, you could basically what's called peak shaving. So look at the next graph, just to give an example. Here's a customer's day load profile. So the bottom white line is, let's say that we want to shave anything above that that white line. So what we do is your battery system will supply the full load, anything above the line, and yeah, so the customer will pay lower on his network demand charge, his network access charge. So typically you can save on those charges during the summer months, while the winter months you could use energy arbitrage. So you can use that as like a business model for his battery system, together with other aspects such as supplying his load or assisting during load shedding. So obviously, battery storage not only have a benefit to the customer itself, but as a utility itself, we're starting to see a lot more variable sources of generation onto the network, and these large utility scale storage has the potential to benefit the municipality or utilities as well. As mentioned, energy arbitrage is one of the aspects where we can basically charge the batteries when the electricity pricing is cheap and then discharge it during peak times. We can use it for spinning and non-spinning reserve, frequency regulation, maybe not so much in the distribution network side. Voltage support, it can be used on networks where you've got weak voltage. Back start capability if you lose the networks. Resource adequacy. So this typically is the ability of the utility to supply or meet the customers or system load demand at all times. So this will obviously assist if during your peak times, if you don't have enough capacity, you can discharge your batteries, whilst the network can feed the customers during normal periods where off-peak times and things. It would assist with transmission congestion relief, because if you can supply the peak loads that will typically congest your transmission lines from the battery systems, it may not require transmission upgrades. So you could defer some of the transmission upgrades. Obviously, that depends on the load and the size of the battery systems. And if using distribution systems, it can defer your distribution network upgrades. So it has many benefits, but as I said, the pricing is currently still too high to justify utilities installing these systems. Although Eskom has plans to install a couple of battery systems, storage systems, so it'll be interesting to see the results and the benefits from those systems there and what it's used for. So there is a company called Enphase that has created what they call a grid forming microinverter. So typically what they are saying is that this inverter will be able to allow you, it'll create a grid or form a grid or microgrid in the sense that should you have a power outage and you do not have battery backup, the inverter would still allow you to generate electricity and feed your load. Obviously, you can only do it during your sunlight hours. So this is quite an interesting inverter or new development. Should obviously be quite interesting to follow. There wasn't too much information on this, but it's quite a yeah. This will definitely help customers during load shedding during the day, etc. But yeah, quite an interesting project. So next, let's look at some of the factors that influence solar PV generation production. So if you're looking at it as a customer, or in terms of how can I improve the production of my PV system? So let's look at some of the factors there. So obviously, if we look at South Africa in comparison to Europe and other countries that have installed solar PV, we see that the irradiation levels in South Africa compares very favorably with other countries in the world. And on average, there is 2,343 hours of sunlight a year, on average of 6.4 hours sunlight a day in South Africa. And the global irradiance for eThekwini is typically 1,625 kilowatt hours per meter squared per year. So if we zoom down to South Africa itself, looking at the global horizontal irradiance, if we compare Durban to a place like Upington, you can see that there's substantial difference in terms of the irradiance. And if we look at the scale on the bottom, we can see Durban is on one end on the left-hand side, while Upington is on the right-hand side. So what does this mean? It means that if you have the same PV system in Durban compared to the same PV system in Upington, your production will be much greater. But in terms of how much, we did a study. So we looked at PV systems in each of the provinces, and we ranked them from the best production from a 1 megawatt PV system installed on a flat roof in each of the provinces, in cities in each of the provinces. And what we noticed is that if you had the same 1 megawatt system in Durban compared to the 1 megawatt system in Upington, or Northern Cape, sorry, to Springbok in Northern Cape, what we find is that there's about 36% more production you would get in the Northern Cape compared to KZN or Durban now. So it's quite substantial. So depending on where you obviously put in the PV system in South Africa, it will affect the amount of production that you get. So let's look at Durban itself, or anyway, as I said, in South Africa, but let's focus on Durban in the sense that what will influence the amount of solar PV? First one is the availability of roof space. As you can see on the bottom left-hand side, this is a mall, and the roof is covered with solar PV. So typically, that's the amount of solar PV they can install. There's not enough space to add more. But on the right-hand side, you can see that the customers are starting to install solar PV on the carports. So they have carports in the carports, and then they add solar PV. Obviously, this has a number of other additional benefits in terms of if you do not have enough roof space, but there's a few other benefits which we'll cover in the next couple of slides. So the other factor, what we find is that these PV panels are pretty heavy here. If you look in the bottom left-hand side, for a typical PV panel, it's about 22.4 kgs for one panel. So depending on the strength of your roof, you could have problems there. I mean, we've seen cases here that the roof collapsed based on the additional weight. You also got to take into account, depending on which country you are or whereabouts you're based, in terms of wind loading, in terms of snow loading, and other factors on the roof itself. But this could be a problem to customers. So depending on what the structural engineer would say in terms of the amount of weight that the roof could take, yeah, so you may not be able to install as much panels as you would want. Yeah. So the way around it is that there is obviously research being done, and new panels which are glass-free and lightweight panels that typically have about 50% the weight of your traditional panel. So you can see your traditional panel is 22.4 kgs, and the new glass-free lightweight PV panel is 11.2 kgs. So these lightweight panels may obviously assist in those cases where your roof is not structurally strong enough to hold the additional weight of the PV panels. Okay, the next factor that will improve the amount of production is what we call your DC to AC ratio of the solar PV system. So typically, what is your DC to AC ratio of a PV system? So your DC ratio is typically the sum of all your panel ratings. If you've got 100 panels rated at 500 watts, so it's 100 times 500 watts, it will give you what your DC rating is. And the AC rating is typically you add up the sum of all the ratings of your inverters. So that gives you your AC rating. So if we look at different manufacturing or brands of inverters, so let's look at the SMA inverter. So it has a DC to AC ratio of 1.5. What does this mean? It typically means that you could install 1.5 megawatts of solar panels or DC panels for your system, and have 1 megawatt of inverters. That's your AC rating, yeah. And your system will work fine, yeah. So you not overload your inverter or do anything else to it. And obviously, you've got to look at which brand of inverter you're using and what is the allowed DC to AC ratio. You can't exceed this or you would damage the inverter. So what would be the effect of increasing your DC to AC ratio as opposed to going 1-to-1, installing 1 megawatt of DC panels versus 1 megawatt of AC inverters? How will it affect production? We did a quick simulation study, and this is how it affects it. So the different colors show that as we increase the DC, so we kept the AC size at 1 megawatt, we increased the DC size from 1 megawatt to 1.1 to 1.2 megawatts to 1.3 and 1.4 megawatts. So we stopped at 1.4 because the inverter had a DC to AC ratio of 1.4. So we didn't exceed it. So as you can see that the monthly production increases, and ultimately it would increase the overall annual production from the PV system. What's interesting on the graph is that during the summer months, you can see that there's much higher production as opposed to your winter and other months around it. So what happens if, in the case, as we said, we've got a DC, we put in 1.4 megawatts of panels, and we've got 1 megawatt of AC inverters. Typically what the inverter will do, and this will happen depending on the tilt angle, the orientation, and whether there's any shading, other aspects. On a really clear day, let's assume that the DC produced is 1.4 megawatts, but your inverter is only rated at 1 megawatt. So what happens is the inverter will basically clip off anything above a megawatt. So you would get the area under the graph, which is basically the total kilowatt hours generated by the system. So this typically would only happen in summer. So let's look at a typical 1 megawatt system installed in Durban. So you can see in summer, this is a summer profile, 1 month profile for between December and January. You can see that the PV system peaks at 1 megawatt a number of times during the month. And obviously, there will be some clipping occurring to get to 1 megawatt on really clear days and when it's not too hot, etc. In autumn, we can see that bulk of the month, the PV system does not generate more than 700 kilowatts for the month. In winter, we can see that you're looking at around 600 kilowatts. 1 or 2 days, maybe it will generate slightly more, but the production is very low. And in spring, we can see that the production is under 900 kilowatts, except right at the end of it, it's starting to increase as it's getting towards sort of summer. So we can see that even with the higher DC to AC ratio, what happens is that only in summer you may get some clipping occurring, but during the rest of the year and other seasons, your production is generally lower than what the maximum rating of your AC or DC is. So you would not exceed, or you'd just end up with additional production with a little bit of clipping within the first few years of your installation of the system. Okay, so the next aspect we'll discuss is the maximum power point tracking. These are typically found on the feature built into your inverters, not built into every inverter, but most of your inverters out there. So in simplest terms, this feature ensures that the solar panels are always working at their maximum efficiency, no matter what the condition is. And it ensures that maximum power extraction from the PV system occurs under all conditions. So if you look at the graph on the left, we can see that you've got a curve in brown, or is it orange? So that's typically your response curve for your current and voltage. And then the blue curve shows the corresponding power, which is basically the sum of your current and voltage. So we see, depending on this, on the point selected on the orange curve, you would end up at some point where you get the maximum power. So you can see that the point selected IMM and VPP, sorry. So it's IMPP and your VMPP will give you the point for your maximum power pointer. So this is done constantly. Or alternatively, if you look on your right-hand side, for your response curve for your current and voltage, what we see is 3 different points are selected, A, B, and C. And each point, if we work out the power, we see that at point B, you obtaining the maximum power. So that's the maximum power point versus the other 2 points where the power output is much lower. So there is advantages of using an inverter with multiple maximum power point trackers versus single. And I think the table shows that there's a number of advantages with using multiple maximum power point trackers in an inverter. And ultimately, it could increase your production between 2.5 to 9% for various different conditions. So you could use inverters with different, with multiple MPPTs for panels installed in different orientations, in cases where you have some shading, where you have temperature losses, or if the panels are not clean. Also, lowers your voltage, startup voltage, so it increases production ultimately. So here's an example of an inverter. This is typically a 60 kilowatt inverter. It has 14 string inputs, but it has 1 maximum power point tracker. So in this case, 10 of the string inputs are used and 4 are unused. And here's another example of an inverter. You have 6 maximum power point trackers with 2 inputs per maximum power point tracker. So as explained previously, not all of the inverters have built-in maximum power point trackers. There is a brand called Solar Edge where they have what they call a power optimizer, which essentially is a maximum power point tracker installed at each panel. So what it does is it would maximize the power output for that panel and ultimately for each of the panels on the string. And ultimately, it will give you better production. It will also help in cases where there's shading. If one panel gets shaded, it does not affect the other panel's production. Because typically in a normal string inverter, if one panel is shaded and is operating at 50% of its capacity, all the panels in the string will operate at 50%. But in the case of the Solar Edge with the power optimizer, one panel is shaded and operating 50%. The rest of the panels that are unshaded will operate at 100% of their capacity at the time. So it obviously has a lot more benefits, and we see it used quite a lot on the network. Also has other advantages such as individual panel monitoring. So you could look for things like if one panel is dirty and on the string, or if a few panels are dirty for some reason. When you start comparing panels on the same string and you're seeing them sort of generating different amounts of power, you could look. Also, if one panel fails, it's quite easy to see on the string which panel has failed. So it has a number of advantages. So the other factor that will influence your rooftop solar PV production is the irradiance, which we obviously saw on the initial graphs between the irradiance in Durban versus Northern Cape, but also within Durban itself, we can see that as your irradiance levels sort of decrease, so does your current, and ultimately it will change the power output that's produced from the panel. So if we're looking at a graph that's plotted, this is actually taken from a PV system. You can see the irradiance for the day versus the power output. So this is a clear day where you've got good irradiance, and you can see your production curve, typically from your PV system in red, typically follows your irradiance sort of curve here. Whereas on a cloudy day where your irradiance sort of changes during the day, you can see the PV system does exactly the same. So there's another example from another PV system where you have sudden cloud cover. And what this does is it results in quite a substantial reduction in production. And it does not give you a nice bell sort of curve. So it gives you this sort of jagged edge curve, which obviously from a network operator point of view, you don't really want that, because what it can do is lead to what we call rapid voltage changes in the network. It's typically similar to losing sort of generation dropping off and coming back sort of, and then the grid taking over. So it starts to change the network voltages. And depending on how often, how frequent it happens, it could cause substantial problems on the network. There's another example of a 1 megawatt PV system on a rainy day. We can see that there's about maximum production is about 20%. Obviously, with rain, there's cloud cover, so, and you obviously don't have the sun out, so your production is very minimal. But what's important to note is you still get some PV production even on a rainy day. Yeah. So the other factor that solar panels don't seem to like is very high temperatures. So what happens when the temperatures increase, the voltages start to drop on the panel, and ultimately it leads to your reduction in the power output of the panel. So you need to take precautions when installing PV panels to allow for spacing under the panel so that hot air can be blown out, cross ventilation. Don't put panels all very close together, large amounts. So these will obviously help and need to be taken into account in your design stages. So what we also need to note is that your PV panels in production reduces over time. Excuse me. So we can see that in year one versus at the end of the life, which is either 20 years or 30 years, it starts. So typically, you can see in year one, they would give you a performance warranty that the plant will operate maybe at 97.5%. And then it basically reduces either by a factor or it's a stepped warranty or linear warranty. So we need to take note that even though the PV system is sized accordingly, it would reduce in terms of the production here. So these are your performance or your guarantees here. But so these you can consider as your worst case sort of production reductions there. There's another example from another solar panel manufacturer. So you have warranties for after 10 years, after 15 years, after 20 years, after 30 years. So what's interesting is that in this panel on the top from the warranty period is after 30 years, your system will still give you almost 85% of the original production. And we can see the one at the bottom, after 30 years, it'll give you 80.6% production. So when I spoke about the sizing of the DC larger than the AC, so as I said, you may get clipping in the first few years, but as the production or the panels degrade in terms of production over time, it would sort of it may counteract that effect. So the other factor is your orientation of your panels to the sun's path and ultimately the inclination angle of your roof. So how exactly does that affect your PV production? So what we did was we simulated different orientation angles and inclination angles of roofs for the same PV system. And we ultimately plotted the graph that's shown on, the table that's shown on the screen. So what we can see is typically your north-facing panels or those closest to your north-facing sort of northeast, northwest, and those around your 30 to 40 degrees or 20 to 40 degrees around there gives you the best sort of production. But the best production is obtained obviously on 30-degree north-facing roof. So this may not always be achieved, but what you can do is try and get as close as possible. So typically, if you have roofs that are north and south facing or northeast and south sort of west facing, you can use those that are more north facing to try and give you better production over the annual production now. So what we find is a lot of installers tend to use the existing building roof inclination and orientation to sort of install their solar panels. So as you can see in this example, the customer just installed it as according to the roof profile. So they didn't take into account that if they change the profile, they could have got more energy, but yeah, so they've done it. So obviously a number of reasons why they would do that is you don't want to tilt or incline the angle too much because then you end up with wind loading under the panels to blow the panels off the roof. So there are a number of reasons. So I'm not sure what was the reason here, but they went obviously according to the roof profile. And in this case, we can see the original roof orientation is obviously not ideal. I wasn't too sure what was the inclination angle, but it had a very fine inclination angle here. Couldn't be more than a few degrees. So what the installer did was they totally changed the orientation and the inclination angle of the panels. They tried to face it more, obviously, north to give it better annual production. So it can be done. So the other aspect which we touched on is obviously if you do not have adequate roof space, you could explore the options of carport structures, which a lot of people have done. And this has a number of benefits. Firstly, with regards to your inclination and orientation of your panels. So with carport structures, unlike your roof, you can basically try and get better orientation angles and you can change the inclination angles to give you better annual production. Obviously, it solves the problem of roof space. If you do not have adequate roof space, you could obviously use the carport structures to give you more space to install panels. If you have problems of structural integrity, the roof can't handle additional panels. It was not built or it cannot carry additional weight on it. The carport structures are definitely a way to go. And with a better tilt angle, it obviously assists with cleaning of the panels during rain, so water can actually run off the panels. And in the case of bifacial panels, which in this case installed on this carport, it allows for better reflection from the back of the panel, so it increases the annual production or energy produced from the panels as well. So it has a number of benefits there. So the other thing that we need to be very wary with when installing PV systems is shading here. Shading can come from obviously walls around the roof, chimneys, air conditioning structures, or as in this case, which is what we call temporary shading, is trees. So obviously, if you trim the tree branches, you could get rid of the shading here. So ideally, it would be good to upfront to sort of either remove the tree or remove the branches that will affect the tree. But this is something that you'll have to continuously sort of trim, but it's temporary in the sense that it can be sort of mitigated against. Ultimately, if you remove the tree, it will get rid of the problem. But I think in this case, the customer wanted the tree. So the other option was obviously to putting the panels away from the tree, and obviously to trim the tree every so often when it started shading the panels. Here's an example of permanent shading, which you can't avoid here. You've got a tall building that's on the path or the path of the sun at some point in the day, and this ultimately shades the customer's PV panels. So obviously this had to be taken into account during the design, and there's a number of ways. Obviously the customer looked at the production figures and saw that it was feasible. He could have obviously added additional panels to try and increase the generation to try and counteract this, but there's an example of permanent shading which you can't, there's nothing you can do about it. Either you accept the losses and install, or alternatively you can't install because you can't move the building. So here's an example of permanent shading, but something that could be avoided. So obviously this was done, they could have avoided this wall because there was shading. So the solution around here was obviously to have maybe not have the last row of panels close to the wall, and that would have helped because you wouldn't get the shading effect. So there's obviously software and that you could use for this customer. What they did was they've used the software. They basically modeled all of the obstructions on the roof, and they basically were able to see which points that they needed to avoid, and then they installed the panels according to that to avoid any shading effects there. So that's the correct way in which you would do the studies if you had obstructions on the roof that could cause shading. So in terms of production, we know that dirty panels obviously do not help with production. So cleanliness of the panels obviously would help with production, and most of these PV systems come with software that you're able to look at the production. So you could see that there is a sudden drop in production on certain strings, etc., which will obviously let you know that panels need cleaning. Alternatively, inclined panels or panels at an inclination angle of maybe 15, 20 degrees, sort of 30 degrees, gives you better sort of panel cleaning when it rains. So as opposed to flat panels or very low inclination angles. Yeah. So you could use that, as I said, with using solar edge technology with power optimizers on each panel. You're able to monitor at panel level. So you can look on the entire string and check obviously why the panels are not performing, if they're all on the same roof pointing the same direction at the same angle, etc. So you want to try and avoid cleanliness of the panel. Make sure the panels are clean. So that may obviously require your maintenance to take place more frequently in certain months, or depending on the area, if there is sand and dust or dirt around. So with the PV panels, it seems to be ever changing in terms of your efficiency of the panels there. I mean, previously the panels had efficiencies much lower than 20%. I mean, now we can see that there's efficiencies that obviously are increasing. On the top, you can see from the panel manufacturer, they've increased the efficiency from 25.82% to 26.3%. There's the other one that still obviously testing is done, 29.2% efficiency. And then obviously on the last paragraph on the page, you can see that they've obviously done some tests in the lab where they have achieved an efficiency of 47.1%. So I think ultimately the efficiency of these panels are starting to increase. I mean, previously what we had to now, there's definitely been improvement in terms of the efficiency. So this means that the panels can generate more electricity for the same size of panels. The sizing of the panels is obviously starting to increase as well. Initially, when we first started off seeing solar PV systems being connected to the network, we saw 250 kilowatt panels are pretty common, but now we're starting to see your panels getting bigger in the 500 watt to 600 watt. Even there's new panels that, although may not be commercially out, but will be shortly, in terms of 700 watts on your right-hand side and 800 watts in the middle. So ultimately, with these bigger panels, it will lead to reduced levelized cost of electricity. Technology, obviously, in the panels have changed. I mean, we've seen a drastic change in the technology. So you're getting what we call new panels coming with half-cut cells. So typically, the traditional panels had 60 to 72 cells. Depending on the panel, you get a 60-cell panel versus a 72-cell panel. But with the half-cut cells, these cells are obviously cut into half. So you're ending up with 120 or 144 cells there. These obviously lead to better production. So what with the half-cut cells is that when the cells are obviously halved, their current are also halved, so the resistant losses are lower and the cell can produce more electricity. So then there's obviously bifacial panels, which you can see on the right-hand side and explained in the carport structures. These panels produce electricity on both sides as opposed to traditional panels only on the side on the top. And so what it does is it increases the overall system production efficiency, and some of the manufacturers claim that it can improve the production by 20 to 30%. Yeah. So obviously these will be ideal on sort of carport structures or things where you can get light reflected from the bottom up or from vehicles or etc. The additional production obviously would vary depending on how it's installed and other factors involved. So in terms of the increase in the cell size, so initially in 2012, we had cells that were 156 millimeters. Then in 2019, these were obviously increased to 166 millimeters. Now in 2020, 2021, we're seeing that the cells increased from 180 to 182 millimeters to now 210 millimeters. So this means that the cells are larger, meaning that they could generate more electricity. And ultimately, the panels become larger, which we saw obviously 600, 700, 800 watt panels that are being produced on the market for the same size. In terms of inverters, we're obviously seeing that the size of inverters are definitely becoming much larger. A few years back, as I said, we've seen systems that were connecting to the grid. Guys were using 17.5 kilowatt. I think the biggest inverters then were about 25 kilowatt inverters. So on a 1 megawatt system, you had multiple inverters there. But now recently, we're seeing inverters like your 110 kilowatts, 110 kilowatt systems. There were 175. There was a 175 kilowatt inverter from ABB. There was a 250 kilowatt inverter from SunGrow, and now SunGrow has obviously introduced a 352 kilowatt inverter. So what this means is that typically if you install a 1 megawatt PV system, you need 3 inverters there. Previously, you would need multiple inverters. So ultimately, it's going to reduce your levelized cost of electricity. So what's interesting to note is that this new inverter comes with 12 maximum power point trackers. We saw the benefits between 1 versus 4 to 6. Obviously, with 12, you're getting much more benefit. It comes with 24 strings. So typically, this means 2 strings per a MPPT. The efficiency is pretty high, 99.01%, really efficient. And the input voltage is 1,500 volts. Traditional inverters were 1,000 volts input, but we're starting to see on the bigger inverters, they're coming in 1,500 volt inputs. These are because your panels are getting larger, and for more panels in the string, your voltage becomes much higher. So obviously there is talk that going forward, the DC input voltage to inverters are going to increase to 2,000 volts to accommodate bigger inverters, bigger panels, and larger size inverters as well. So I think locally that there is a company called Art Solar that does assembly of PV panels. They're located in New Germany. So they're currently assembling panels that are, I think, 540 watts, the big ones, and efficiencies of 21.3%. So might be, if people are interested, is to do a field trip there if you want to see how panels are assembled. So this is not typically manufacturing as in creating the wafer and everything else, but actually assembling.
Yeah.
Prof? Okay, so
yes, I just confirmed that we'll make such a visit.
Yeah, that'll be an interesting one for the guys, definitely. Okay, so let's look at some of the solar PV opportunities that are available within Durban or other municipalities. So in terms of your house, as I said, you could use solar roof tiles as opposed to normal tiles. Then there is what's called building integrated PV systems. So on high-rise buildings, you typically don't have much roof space there. So based on the building load, you may not be able to put too much of panels. But building integrated PV systems, you could basically replace all of the windows with PV panels, or specially designed PV panels that you could be able to see out of it and be able to produce energy. Obviously, based on the angle and, as I said, on the curve on the table previously that we looked at, may not give you the best production, but it obviously gives you much more area and you can put in much more panels. Then we touched on that your new glass-free panels are typically half the weight of what the traditional panels would be glass top had. And there's obviously new lightweight panels, which we see as well, that are flexible and lightweight, that could be hung on the side of buildings or put at various places that will allow solar generation on roads and pathways. So I think there's lots of opportunities there. In terms of traditional solar farms, there's obviously opportunities for those. But I think in Durban, we had a 0.5 megawatt solar farm, but I think the problem with the medium to large scale solar farms, they require large plots of land, which obviously has to be located close to the municipal grid. And the challenge is that large plots of land located close to the municipal grid is expensive. Land is not the cheapest of things in Durban, and for PV system farms, you need large plots of land, so it's not readily available. So in other places, yes, you could get land, but I think in Durban, it's a bit difficult to get land for large farms, yeah. So we got to look at alternatives, yeah. So what we did some studies and looked at in terms of large plots of land close to the grid connections, yeah. And we realized that at the municipality, we had more than 20 closed landfill sites, yeah. So these are typically municipal owned. They're located really close to the grid connection. They're large tracts of land. And we typically had limited usage for the land because of the waste would settle and you can't really build anything or etc. on it. And a very low value, which could be leased from the municipality. So we did some studies and we realized that we could install solar panels on these closed landfill sites, on some of the sites, the bigger sites, and we could generate about 53 megawatts of electricity. Then the other alternative we looked at is we have a number of water reservoirs around the city here. So these typically have a nice flat top, and lots of them are located on hilltops to allow for water flow, etc. So we could install solar panels on top of these water reservoirs here, typically unused space here. And I think we looked at some of the projects here. We could generate close to 10 megawatts of electricity from these projects here. So there are some of the opportunities that obviously you could use as opposed to traditional sort of solar farms here. There's obviously the potential for floating solar systems if you've got large rivers, lakes that could be used. And I think with floating, it also helps with the case of evaporation of water. It also, the panels are much cooler, so you wouldn't have much of the temperature problems. So it allows them to operate more efficiency and produce better generation. Okay, maybe let's just touch on some of the challenges before we round up. So I think some of the challenges is this is just one area in eThekwini, and we're starting to see a large number of PV systems coming up here. So this is obviously not a problem during the normal workday. If we look at the normal workday, this is a typical customer's profile with his PV generation, uses all of the electricity, zero export to the grid. So there's no real issue. The problem comes in on a weekend where these companies are closed down. Weekend, public holidays, election days, December holidays, they tend to export bulk of the electricity to the grid. Now, if everyone is doing that, you do not have adequate load and you end up with lots of problems such as voltage rise, etc. This is the case with, we did some studies for another project, and you can see that as you tend to increase the amount of generation that you put into the network with with lower loads there, you start to end up raising the voltages on the network, and you can exceed some of your limits and cause problems on the network. So the other problem that we find is that we've got what we call a SCADA system, or it's called supervisory control and data acquisition. So our network control officers would obviously look at the network, look at what the real-time loading is. But I think now with large PV systems, batteries, other sort of generation systems, they're not really getting a true picture. So this is looking at the customer's PV system with his load profile. So typically what the control officer would see is the red part of the curve. That will be the loading that will be brought back into the network, or what you will be able to see, but you wouldn't see the customer's full sort of load itself. Even from a planning perspective, when you're recording the customer or network load profile, you're not getting a true reflection because your PV system or whatever generation system that you're using sort of distorts the curve here, which you obviously need to take into account because it could lead to incorrect planning and overloading of the networks, etc. So the other problem is, as explained previously on this curve, before load shedding, you got portion of the load fed by the PV system and portion by the grid. But when load shedding comes, you basically everything goes off. But once the grid returns, the PV system will not come back. So all of the customers' startup load, etc., need to be the grid needs to be able to feed that and take that up before the PV system can synchronize and come back on there. So that's a critical thing that needs to be taken account, especially with larger PV systems coming into the network. So in terms of planning, ultimately, you still got to plan for the customer's full load, irrespective of the PV system he has, because as I said, when you switch back on after load shedding and outage, you still need to feed the customer's full in-rush current, full startup load, until the PV system can come back in there. Then there's obviously revenue loss on bundled electricity tariffs. So these typically are on your small business and your residential customers. So what does this mean is that the customers pay a flat rate, such as on your residential tariff, you pay 240 per kilowatt hour. There's no fixed charges. So of that 240, a portion of it goes to your energy costs that goes directly to Eskom. So that's typically about 65% of that 240 goes to Eskom with direct pass-through cost. The other 35% typically goes to your overhead costs, which include your admin costs, maintenance, network costs, replacement of stuff on the network, upgrading network, staff salaries, and all your overhead costs there. So what happens when the customer installs solar PV is that the PV system will generate electricity. Typically on a 1 megawatt system, it'll generate about 1.5 million kilowatt hours a year. So what it means is, as a municipality, we end up selling less electricity to the customer. So we're unable to recoup the fixed overhead costs, which obviously are fixed costs irrespective of the amount that the customer uses, because you still need to make the network available. As I said, after load shedding or something, you still have to feed the customer's full load. So that's a challenge. And obviously, in the case of, we've got a lot of prepaid customers as well. So it's difficult. Even if you introduce new tariffs, those prepaid meters will obviously not be able to administer those tariffs. The other challenge is that we've got a lot of old disk meters, and these tend, when the customer is feeding back into the network, especially on the residential and small business side, the meters turn backwards. So essentially, it means one-to-one net billing, and it's obviously a revenue loss there. So what going forward we need is obviously 4-quadrant digital meters that can be programmed for different registers, etc. But obviously, these are more costly meters. And it needs to be rolled out, considering the municipality have about over 750,000 customers. And then you've got the aspect of wheeling of electricity. As explained, we've got, if you build a PV farm in the Northern Cape versus KZN, you end up with much more production. So what the customers can do is either put in a farm in a more suitable area and wheel the power by Eskom and eThekwini networks to themselves, or alternative, they can buy from someone outside the municipality and wheel the power. But in the case of wheeling of electricity, it's more a financial transaction, as opposed to physically the power coming from there to the customer itself. It gets absorbed pretty much around where it's injected into the grid. Yeah, so it's more a financial transaction, but as I said, it needs to be taken into account. You need to have tariff for sort of wheeling of electricity, etc. And obviously, from a municipality or any utility, there is a risk of customers going off the grid. Yeah, so I think we're starting to see a lot more customers installing battery systems to try and allow them to ride out load shedding and network outages. But I mean, nothing stops customers from installing more batteries and ultimately going off grid, because at the moment, lots of customers are taking off their cooking load and using gas. Guys are using gas geysers, solar geysers, heat pumps. So they're reducing their load through energy efficiency, LED lighting, etc. So it may not take too much, especially on the newer lithium-ion batteries. You get some really big batteries. So 2 or 3 of those batteries could take a customer off the grid. Yeah. And ultimately, with all of these sort of generation technologies, we would definitely need a smart grid to connect and obviously manage all of these things, as opposed to how traditionally we manage things. So I think going forward, we definitely need a smart grid to manage all of these different sources and storage options to be able to do that. Okay, to conclude, so we covered, I think, a lot of aspects, and what we're saying is that renewable energy outputs are intermittent and dictated by the primary energy source, resulting in the customer importing and exporting energy at any time, which obviously need to be carefully managed by the municipality. And power quality problems such as voltage rise, harmonics protection, stability problems can arise if not managed correctly by the utility. We covered the driving factors that are increasing the uptake of solar PV and other forms of small-scale embedded generation, and obviously maybe in future batteries as well. I think, as we mentioned, that revenue loss is a concern, so the municipal business model needs to change to ensure business sustainability going forward in the future. And we did say that smart grids are essential for the management of all current and future technologies in the grid. And I think with the reducing cost of battery storage, we'll see more battery storage being installed going forward. Thank you.
A very big thank you, Dr. Sewchurran, for the presentation. A lot of things. I've been trying to raise 200,000 rand or more to do my household PV system. Now I realize that I can go to Netbank and I can get a system that can save me from going to raise all that capital and save pennies to get there. So thank you very much. There's a lot that has come in. Now I do have some questions here, but I'm going to open to the floor for any comments, questions first from the audience. Please, can you go ahead, please? Just, I think I can see hands. Okay. You can please go ahead and let's see if you have any questions or comments for for the session. Anybody, please, just go ahead. Just raise your hand, and let me see how many people have questions. There's a little icon you can touch there that will show that you want. Yes, Dr. Musasa, Dr. Kabea, please go ahead. Please, question. Unmute, sir.
All right, thanks, Prof. Thanks also. Thanks, yes, Doc, for the presentation. I really like it. So my question is about I'm a bit concerned of the graph. There was a graph that you present for the load shedding, which when there's a load shedding and the PV system went off the same time. So I would like to know what is the grid code requirement in that condition, in that case, for this independent power producer. In case of load shedding, should the PV remain connected or disconnected from the grid? Can you explain?
That's a good question. So what I showed on the graph was a typical customer, so a typical mall within the municipal.
Oh, okay.
It's not your large IPP farms, because those guys are contracted and you'd want them onto the grid, yeah. But in terms of safety on the local network, you typically you don't want anti-islanding. So You want the customer to switch off so that he can't backfeed and obviously hurt and kill people working on the network. But there are cases where the customer will obviously disconnect from the network and you'll run in a sort of island mode, but he first has to disconnect before he can go that route. If they bring in standby generators and then bring in the PV, etc. I'm not sure if that's clear.
All right.
Yes.
Yes, it's clear. So at least because it's about smart grid, I would like just to know about, is any in standard grid code which refer to the load shedding? We always have grid codes for many steady state operation in case of fault. What about load shedding? Is it there something, a statement which we rely on when we're installing the PV system?
Okay, so in terms of the grid code, there is no grid code for load shedding in itself.
Okay.
But there is an NRS document, I think it's 048 part 9, I can't remember which part it is, but that talks about load shedding and what happens there. But in terms of normal, if you put a PV system in your house or building within the municipal network, so typically NRS 097 will talk about it does not allow you to anti-island, meaning that you can't operate in island mode and try and while you're still connected to the grid, etc. So I think from that perspective, yeah.
Okay, thank you.
Well, just to follow up on that question, my question there is that if I recall, the minimum size of your installation should be 30 kilowatts and not exceeding 1 megawatt, isn't it?
Sorry, for what is that from?
No, for your household installation or independent installation without being an IPP, between 30 kilowatts and 1 megawatt, isn't it?
It's actually changed now, so you can go up to 100 megawatts.
Oh dear, that's heavy.
It just changed a month or two back, yeah.
Okay.
So that is why we're finding on our graph, we're getting a lot more applications and a lot bigger applications are.
Okay, my question actually is this. If we decide that we want to put up a system or multiple systems linked together up here in the Faculty of Engineering.
Yes.
My rough estimate from my head is that we can actually have a 30 kilowatt system here in the department, and we take care of a number of our lighting loads and not of course those big laboratories. But if we really want to go the extreme distance, we might be looking at maybe going for a megawatt for the faculty when you now want to take in some significant loads in the labs. If we're to take that step, can we commercially implement that project, secure a loan from NetBank, implement it, have it paid back and arrange the investor and all that? Is that possible?
Yeah, that is possible. As I said, they will assess based on risk. There's obviously the other option, you could get an installer to come and do it and just sign a PPA with him. So there's various options there. But yeah, the bank loan is obviously one of the options there.
Okay, and thank you for that. That's a very good insight. You see, the reason I brought this up is because as a university, we have active research work going on. And for me, I feel that one of the things the faculty should be doing is expanding its technical capacity, hiring professional engineers and other people who are part of your entire team. So you can actually embark on projects that you don't have to necessarily outsource them completely, but you can also have, for example, we have this little 15 kilowatt system right here. And the network operator is literally our technician who, who monitors the entire system, switches it, in different modes and based on whether we have load shedding or whether we have poor, insufficient supply from the PV system, and have to back it up with battery supply. Because we have a PV system here with a battery, with a BSS as well. In our case with the grid tied, system. So that's why I'm asking that question. The question that I had, which I wrote down here, was if you can help us in this area, fine. If not, we can always discuss it later on. What research projects or opportunities exist for solar PV grid-tied inverter system from the sharp edges, switching from one mode to the other mode, time taking? Just like you have UPS those days, there's a small blackout and all that. You can keep your computers working until whatever backup you have kicks in and all that. If you can give us any idea of what you think would be areas of little gaps that can be explored in terms of research, do let me know. And then the other one I mentioned here was, a project, for example, can be the use of your battery storage system to supply at high tariff peak time and discharge at, to supply the load or the grid at tariff peak times and then charge the battery at low tariff time. So that could be a nice project where you can use some AI tools and real-time information of tariffs and so forth, and build a system whereby it can discharge at this time or at this under these conditions. And then, of course, I don't know how that will be done, but there'll be a lot of need to monitor stuff and use some ICT facilities and so forth. But that just came across to me that it could be a useful project to look at. To design a system for charging and discharging batteries for both high and low tariff or low price periods, just like you also deal with your demand response. What do you think? Any other comments from anybody else is welcome.
Coming there before the others come in is that I did speak to some of the large battery manufacturers previously, and a lot of the battery management systems does allow you to basically put in when do you want to charge, discharge, and a whole lot of parameters. You can set it in the system itself based on tariff or peak shaving, etc. So I'm not sure regarding the algorithms within it, but I think
yes,
it is commercially available. But obviously, it'd be good to get research done and sort of into it how best in terms to optimize your your battery.
That's a research problem. Thank you very much. Any other questions, please, from anybody else? Before we wrap it up, I want to thank Doctor for such a brilliant. Okay, let's see, Dr. Tunji, quickly.
Okay, thank you so much. Yeah, I want to ask a question as regards the, it's a follow-up question on what the question Dr. Kabaya asked regarding the load shedding at the peak time. And you mentioned something that it's possible to for the customer to go off grid at that time in order for them to be able to use their grid-tied PV. So I just want a clarification. So are you trying to say that it's possible for us to bring in diesel generator, for example, and still continue to use the PV system, so that the diesel generator will serve as the grid? Then, if that is possible, what is the economic implication? Is it, in terms of the fuel cost, are we going to reduce fuel costs at that time? Then the second question is that you talked about customers going off grid being a challenge. I don't know what's the impact of having many customers going off the grid. Is it actually a challenge or not? So that is the question I am asking the guest lecturer. Thank you.
First one, we don't allow the customer what we call anti-islanding, in the sense that his PV system has to switch off when the grid switches off. But what happens is we allow customers to, like those guys that got diesel generators, what they have is a changeover switch, where the load could only be either fed from the grid or either from the diesel generator. So, but not both there. So there's no risk of basically feeding back to the grid. So what we see is a lot of the customers, when the grid goes down, they basically switch it off the grid and they change over to the diesel generator. Diesel generator will start up. So when the grid goes down, the PV would obviously go down. And then when the diesel generator is up and running, the PV can then synchronize, and because it's typically using the grid or the diesel generator as a reference point. So definitely, if it comes back on, it will reduce your diesel consumption, because if your load, the only thing with the diesel generators is, from discussions, is that you can't run them below, most of them below like 30% of the rated capacity, because they get very unstable, etc. So you have to manage your PV system such that either the PV system is not too large, or alternatively you manage it in terms of curtailing the amount of power that it's supplying. So the diesel generator always supplies at least 30% of the load, and then the rest can be supplied by the PV. So it'll be sort of a load following thing. It can happen, and we've seen many of those installations where the guys are obviously trying to save on their diesel generator cost. The second aspect in terms of customers going off grid. So I think the risk here is more on your residential and maybe a very small business sort of customers, where you'll find them going off grid because all they need is a few batteries typically and your PV system to supply their loads, as opposed to your large industries and things. It'd be difficult. So where the risks come in, we have a few customers, but I mean not substantially compared to our customer base of over 750,000 that have gone off grid. But what the problem comes in is that with the tariff increases, it becomes more feasible for obviously putting in battery storage coming down, PV costs coming down. It becomes more feasible for guys to put in these systems and ultimately go off grid. So I mean, all it takes for now for customers to go off grid, especially on the residential side, is cheaper battery storage systems. So I think going forward, with rising costs it is definitely a concern.
Yeah, I think also one of the things that people are also concerned about with going off grid is that if you have any significant problems of your own internally, or you have to replace an inverter, for example, another equipment, you might end up going many days without any power supply because you're no longer serviced by eThekwini. Okay, let me take a last question from Dr. Ibiemi, please. Yes. Unmute, sir. Thank you.
Thank you very much, Prof. I want to thank the lecturer for opening up these opportunities and, of course, taking us through the activities going on just around us. My question is first on the comment Prof made on identifying funding opportunities for individuals that are interested. I just want to ask that are there roles the departments can play in driving the campaign down to people who may be interested in having solar systems driven from their individual homes? Are there roles the department can play? My second question is on the entrepreneurial opportunities. What are the entrepreneurial opportunities for our students? Since there is an increasing interest and potential, of course, of using the solar systems now to complement the power from the grid. What are the entrepreneurial opportunities? How do they come in? Thank you.
Thank you very much. Over to you, sir.
Maybe just coming to the first question. So the municipalities obviously allowed customers to connect, but there obviously is rules and regulations in terms. It has to be safe and not cause problems in the network. So there is an application process that needs to be followed. So once you make an application, it's assessed, and in terms of size, in terms of the equipment used, in terms of safety aspects. And once it's accepted, you're given a go-ahead, and then you'll be able to connect onto the network. So obviously, the municipality has, which I didn't cover too much as well, is that introduced what we call in feed-in tariffs. So what we're doing is you will be compensated for the energy that you export to the grid, and but there is obviously a network access charge which you pay, and the fee that you obviously get for exporting to the grid is different from what you pay for importing from the grid. So from that aspect, I think you're good in the sense that there is rules and regulations, and it's allowed here. We have a number of customers connected to the grid here. So that's the one aspect. The second aspect is in terms of skills for the students here. So obviously this is a new area, and there is a lot of growth in this area. So in terms of jobs or things students can do is obviously get involved in as solar designers, solar system installers, get involved in the maintenance side, in the battery side. So there's lots of scope in these areas. So obviously they will need additional training, etc. There is training such as the PV green card training, where it's accredited training where people have to go and they are assessed in order to be able to do these things. and sign-off systems. Obviously, you need your PR registration from the Engineering Council of South Africa. But definitely, there's a lot of scope in these areas.
A very big thank you, Dr. Sanjeeth Sewchurran. Thank you so much for really opening our eyes to a lot of things that, both from the business point of view, entrepreneurship, technical, and of course, the importance of this very subject, and like the last question I raised, things happening around us that we need to be more aware of, and the need for us to take this not just across only to all various departments and the university at large and campuses, but even to our communities, and even though the municipality might be losing revenue as a result of some of these projects, but I think it also gives room for additional capacity for more industries, more companies, more factories, more manufacturing concerns to rise in this region and be bigger, which are the big, large employers of labor. So that is the balance. We need to have more manufacturing, more other major businesses in the area, served by eThekwini. I want to thank you so much for the time. Thank you so much for sharing your work with us, and it is just central to our thinking and some of our activities here in the Smart Grid Research Center, in this department, and of course across the DUT in many regards. I just want to thank you so much for the time you have taken to be with us and to share with us. You are one of us too, in a sense, but we also recognize that you have a big role out there in industry, and we want to thank you so much for your contributions to various structures in the country, as well as with the National Electricity Regulator as well, where you do also play a role in terms of other services and support to that organ, within our entire electricity industry. So Dr. Sanjeeth, on behalf of all my colleagues, the center, the department, students, staff, postdocs, I want to thank you for this presentation. As a little way of appreciation for this time out and so forth, we have a token gift, which I will just ask Ms. Namusa to ultimately just connect with you directly